We will continue our study of continuity and one-sided limits by analyzing continuity in piecewise defined functions. In this example, find any discontinuities and determine which type. Justify your answers with the definition of continuity. We are given that g of x is equal to the absolute value of x plus 7 over x plus 7. Now, a quick reminder that absolute value is a piecewise defined function. So, for example, if we had the absolute value of a, that would be defined in two pieces. It's the opposite of a whenever a is less than 0, and it's a whenever a is greater than or equal to 0. So then our g of x is going to have to be written as a piecewise defined function, and it's going to be the opposite of x plus 7 over x plus 7 whenever x plus 7 is less than 0, and that will happen when x is less than negative 7. Or the other piece is it will be the positive version, so x plus 7 over x plus 7. Now, normally in the definition, we say that it's equal to a when a is greater than or equal to 0. But in this case, because x plus 7 is in the denominator, and the denominator can never equal 0, we have to say that this will happen when x plus 7 is strictly greater than 0. And of course, that will be when x is greater than negative 7. Now we've taken g of x and written it as a piecewise defined function. Now, something very handy to do when you have a piecewise defined function is to write the pieces of the function on a number line. Now, we see that this function changes over at x equals negative 7. So let's put negative 7 on our number line. And we know that when we are less than negative 7, over in this region, we have to use this piece of the function. So it will be negative of x plus 7 over x plus 7 when we are to the left of negative 7. And when we are over here, when x is greater than negative 7, we know that it's this definition, which is x plus 7 over x plus 7. So because g is a rational function, we know that it's going to be continuous on its domain. So g is going to be continuous from negative infinity to negative 7, union negative 7 to infinity. So then our job is to analyze what happens at the x values that are excluded from the domain and see if we have a discontinuity, and if so, what kind. So in this case, we will want to look at x equals negative 7. We have to apply the definition of continuity. Step 1 says we need to look at the function value. So here in step 1, we need to find g of negative 7. And of course, that does not exist. And now because g failed at step 1, we already know there's going to be a discontinuity. we will need the limit to figure out which type. So let's go on to step 2, which tells us to find the limit of the function. Now, in step 2, we actually have to find a two-sided limit, but because we have a piecewise defined function, we can see right away that the limit coming in from the left is going to use a different definition than the limit coming in from the right. So that's our signal that we can't do the two-sided limit directly, and we need to do the one-sided limits. So if we start off with the limit as x approaches -7 from the left, then we have to use this definition of the function, the opposite of x plus 7 over x plus 7. Now within the limit, we know we are allowed to cancel the common factor, so this becomes the limit as x approaches -7 from the left of -1. And we know that to evaluate a constant function, the limit just equals that constant function, so this limit is -1. Now, if we do the limit as x approaches -7 from the right, we have to use this piece of the function, so we get x plus 7 over x plus 7. Because we are in the limit, we can cancel out the common factors. So this is going to equal the limit as x approaches -7 from the right of +1, and that limit equals 1. Now, because the limit from the left does not equal the limit from the right, therefore, we say the limit as x approaches -7, remember this is the two-sided limit of g of x, does not exist. Now, because the limit does not exist, we have to conclude that g has a non-removable discontinuity at x equals -7. Now, similar to the argument we made for polynomial functions and rational functions, we can show that radical functions are continuous on their domains. For any radical function f of x with x equals c in its domain, we know that f of c exists. Now that satisfies step 1 of the definition of continuity. Using direct substitution, we get limit as x approaches c of f of x will equal f of c. We know that f of c exists everywhere on the domain. Therefore, this limit exists everywhere on the domain. So that satisfies step 2. And since the limit value is equal to the function value at every c, then that satisfies step 3 of the definition. So because steps 1, 2, and 3 are satisfied at every value of c in the domain, we know that radical functions are continuous on their domains. In this example, find any discontinuities and determine which type. Justify your answers with the definition of continuity. We have a piecewise defined function here for h of x, and the changeover happens at x equals 3. So let's get that on our number line. Coming into 3 from the left, we would be using this piece of the function, which is x. And coming in from the right, we would be using this piece, which is square root of x plus 6. Now, let's look at each piece separately. We know that h of x, the part where it equals x, well, that's just a line, which is just a very simple polynomial function, which is continuous everywhere. So far, we know h is continuous from negative infinity up to 3. Now, we don't know exactly what's going to happen at 3 at the changeover point. So let's now look at this piece right here. Square root of x plus 6, we know that radical functions are continuous on their domains. So as long as we stay within the domain of this radical function, we know this piece will be continuous. Now, the domain of this square root of x plus 6, we know we need x plus 6 to be greater than or equal to 0, which means x has to be greater than or equal to negative 6. So as long as we put in values that are greater than or equal to negative 6, then this part of the function will be continuous on the interval from 3 to infinity. Each piece on its own is continuous for the x values that we're inputting. So the only thing in question is at the changeover point where x equals 3. So that's what we will look at. So the definition of continuity, step 1, says we need to do h of 3. H of 3 means we're plugging into this piece. If we put that value in there, we're doing the square root of 3 plus 6, which is radical 9, which is 3. So far, so good. H of 3 exists. In step 2, we have to look at the limit. And although we have to look at a two-sided limit, we know now anytime we have a piecewise defined function, we need to look at the one-sided limits. So the limit as x approaches 3 from the left, we know we have to use this piece, which is x. We can do a direct substitution, and this limit is equal to 3. Now we need to look at the limit as x approaches 3 from the right. This time, since we're coming in from the right, we have to use this definition of the function, which is square root of x plus 6. Once again, we can do direct substitution, and if we plug that 3 in for x, we have the square root of 9, which is equal to 3. Now, in this case, the limit from the left was 3. The limit from the right was 3. Therefore, the limit as x approaches 3 of h of x, now of course this is the two-sided limit, also would have to equal 3. So now we've satisfied step 2 of the definition of continuity. Then we go on to step 3, which says that the limit value needs to equal the function value. We know that the limit is equal to 3. The function value is equal to 3. So we have that the limit as x approaches 3 of h of x equals h of 3. And what these 3 steps prove, so by 1, 2, and 3, h is continuous at x equals 3. So now we can combine these results. This work here showed us that h was continuous at the single point of x equals 3. We already knew that h was continuous everywhere else from analyzing the piecewise function. So combining those two, this tells us that h of x is continuous for all values of x, which is negative infinity to positive infinity. Or another way we can say this is h is continuous everywhere. Remember, we learned a little definition earlier where if a function is continuous on the open interval from negative infinity to positive infinity, we can say that function is continuous everywhere. In this example, apply the definition of continuity to find a and b so that f will be continuous for all values of x. We are given this piecewise defined function here. We see that it changes over at -2 and +1. So let's get those values on the number line. For this piece of the function, we see that f of x is going to equal 8. When we are in between -2 and 1, f of x will equal ax plus b. And when we are greater than or equal to 1, f of x will be x squared plus 1. Now, on their own, each of these pieces is continuous because f of x being 8, or ax plus b, or x squared plus 1, all of those are just polynomials, and we know that polynomials are continuous everywhere. So what we have to show is that the function will be continuous at the places it changes over at -2 and +1. So let's apply the definition starting at -2. We will need to evaluate f of -2, and that goes into this top piece here, so that's equal to 8. And then, for f to be continuous, we know that the two-sided limit going to -2 has to exist and will also have to equal 8. But because this is a piecewise defined function, we can't do the two-sided limit directly, so we need to do the two one-sided limits and make sure that they will equal each other. So if we look at the limit as x approaches -2 from the left, that means we are using this piece of the function, which is 8. That's going to have to equal the limit as x approaches -2 from the right, which is using this piece of the function, ax plus b. Now we can evaluate both of these limits. This first one is just 8, and that has to equal. For this second one, we can do a direct substitution, and this is just negative 2a plus b. Now we need to do the same analysis over here at x equals 1. So f of 1, we know would get plugged into this bottom piece. 1 squared plus 1 is equal to 2. Now for the function to be continuous, we need the two-sided limit going to 1 also to exist and to be equal to 2. Since we can't evaluate the two-sided limit directly because we have a piecewise defined function, we have to look at the one-sided limits and make them equal to each other. So coming in from the left, we would have limit x approaches 1 from the left of ax plus b, and that's going to have to equal the limit as x comes in from the right of 1, which would be x squared plus 1. Now both of these limits can be evaluated using direct substitution. So we put the 1 in for x, and this becomes a plus b equals, on the right-hand side, we put the 1 in for the x, and this becomes 1 plus 1, which is 2. So now we have two equations with two unknowns, and you learned how to solve these in your algebra class. Let's call this equation 1, and we'll call this one equation 2. If I start with equation 1, I'm going to write this side first. I'm going to say negative 2a plus b is equal to 8. Now we know that we're going to want to eliminate a variable. So what I'm going to do is take the opposite of equation 2. So then that would be negative a minus b is equal to negative 2. Now I can add these two equations up, and we get negative 3a. The b's are going to cancel. That's why we subtracted the second equation, equals 8 minus 2, which is 6. Then dividing by negative 3, we get that a is equal to negative 2. Now to find b, we just need to plug into either of the equations. Equation 2 is the simpler one, so let's just plug into equation 2, and we have negative 2 plus b is going to equal 2. We add 2 to both sides, and we get b is equal to 4. So now we have found a and b so that this piecewise function will be continuous everywhere. So we have a equals negative 2 and b equals 4. Next up, we have continuity on a closed interval. F of x is continuous on the closed interval from a to b if all three of these conditions are met. First, f of x is continuous on the open interval from a to b Remember that a closed interval means the endpoints are included, and an open interval means the endpoints are not included. Second, the limit as x approaches a from the right of f of x has to equal f of a. So that means the one-sided limit here, coming in from the right at the left endpoint, has to equal the function value at the left endpoint. Another way of saying that is the function is continuous from the right at a. Third, the limit as x approaches b from the left of f of x has to equal f of b. So that means as we're coming in from the left at the right endpoint, that one-sided limit has to equal the function value there. Another way of saying that is the function is continuous from the left at b. I think looking at an example will help you understand how this works. Here, we have to use continuity on a closed interval to explain why f of x is continuous on the closed interval from 1 to 3. So let's walk through these 3 steps. First, we have to decide if f of x will be continuous on the open interval, in our case, from 1 to 3. Now, by looking at the graph, for all the points in between 1 and 3, there are no breaks, jumps, holes, asymptotes. There's nothing that would cause a discontinuity on the graph. It's what we call a smooth curve. So, because we have the graph, we can say, by the graph, f is continuous on that open interval from 1 to 3. We can visually inspect the graph and see it. Another way you can think of it is that for all the points between 1 and 3, you can draw the graph without ever having to pick up your pencil. And that's what a continuous graph looks like. Second, we have to show that the function is continuous from the right at x equals 1. So that means we need to do the limit as x approaches 1 from the right of f of x. And we can see that as x comes into 1 from the right, the y value is approaching 2. Now we also have to evaluate f of 1, and we see that f of 1 has a point at a y value of 2, so this is equal to f of 1. So we have satisfied step 2 of this definition. And we have shown that f is continuous from the right at x equals 1. Third, we have to do the limit as x approaches the right endpoint, which is 3, from the left of f of x. Now, as x gets closer and closer to 3, coming in from the left, we can see that the y value is getting closer and closer to 4. And that's also the function value at x equals 3. So that equals f of 3. So we just showed that this f of x is continuous from the left at x equals 3. So by steps 1, 2, and 3, f is continuous on the closed interval from 1 to 3. And this was just a simple example to help you understand this definition. Here we look at continuity on intervals that are neither open nor closed. Combining the definition of continuity with continuity on a closed interval, we find that functions can also be continuous on intervals in the form where the left endpoint A is included and the right endpoint B is not, or the left endpoint A is not included, but the right endpoint B is. These are sometimes referred to as half-open or half-closed intervals, as well as infinite intervals, such as the interval from A to infinity, where the left endpoint A is included, or the interval from negative infinity to A, where the right endpoint A is included. In this example, name the intervals on which each function is continuous. Here we are given the graph of h of x. There's a vertical asymptote here, and we can see that the function approaches that vertical asymptote, but remember it never crosses it. So what we would have to say here is that h of x is continuous for x on the interval. We would put a closed bracket and we would include the x equals 1. Then it goes all the way until 3, but does not include 3. So we have to put an open bracket on the 3. For this f of x, we would say that f of x is continuous for x belonging to the interval. In this case, the left endpoint is not included, the right endpoint is not included, but all the points in between 5 and 15 are included, so this would be an open interval from 5 to 15. And now for this g of x, we would say g of x is continuous for x on the interval. Now for this graph, we will have to write it in two pieces. We can see that x equals 4 is included, and then every point between 4 and 8 is included, but at x equals 8, we have to exclude that point. So we would put a hard bracket, 4, 8, with an open bracket, union, then it would start again immediately after 8, so that's an open bracket, 8, and then every x value is included from there to infinity. This goes on forever and ever, so we put infinity with an open bracket. Now there's a couple important differences to notice here. This interval goes off to positive infinity because the x value on the graph goes to infinity. And that's different than this graph over here of h of x. It's the y value that's going off to infinity here. The x value never goes past 3, and that's why the right endpoint has a curved bracket on the 3. Remember that when we're talking about where something is happening, we're always talking about the x values. That's why we're specific to say that x is on the interval from 1 to 3, where the 3 is not included. Where over here on this graph, on this piece of it, x started at 8, well, actually just after 8, right? Because x equals 8 is not included. And then the x value goes off to infinity. In this example, state the interval where the function is continuous. As a hint, recall that radical functions are continuous on their domains. So given f of x is equal to the square root of 2x minus 5, we know that f will be continuous on the entire domain of this function. So then let's analyze the domain. We know that what's underneath the radical, 2x minus 5, has to be greater than or equal to 0, which means 2x has to be greater than or equal to 5, which means x has to be greater than or equal to 5/2. So as long as we pick x values in the domain, this f of x will be continuous. So we can say that f is continuous for x on the interval, hard bracket, 5/2 to infinity. In this example, state the interval where the function is continuous. We are given g of x is equal to 1 over the square root of the quantity 13 minus x. We know that radical functions are continuous on their domains, and so are rational functions. So we need to look at the domain here. Now, normally, what's under the radical has to be greater than or equal to 0. But since this radical is in a denominator, it cannot equal 0. So we have to solve 13 minus x has to be strictly greater than 0. Subtracting 13 from both sides, we have negative x is greater than negative 13. Multiplying both sides by -1, we know we have to switch the inequality symbol, and this becomes x is less than 13. So g of x is continuous for x on the interval from -infinity to 13, not including the 13. In this example, state the interval where the function is continuous. We are given h of x is equal to the square root of the quantity x squared minus 4. We know that radical functions are continuous on their domains, so let's take a look at this domain. We need x squared minus 4 to be greater than or equal to 0. Now, to solve a quadratic inequality, we need to factor the left-hand side into x plus 2 times x minus 2 is greater than or equal to 0. Now, to solve this, we need to use a number line. And we put the roots on there, -2 and +2. And then we make use of test points. So in this interval, a test point could be -3. So if we put -3 into the first factor, we would have a negative times. If we put a -3 into the second factor, that would also be negative. A negative times a negative is a positive. So when we are in this interval here, this product will be positive. Picking a test point on this interval is pretty easy. Our favorite one is 0. If we put 0 into the first factor, we get a positive number. If we put 0 into the second factor, we get a negative number. A positive times a negative is a negative. So that means for all points between -2 and 2, this product will be negative. On this interval, we pick a test point, say 3. Plugging that into the first factor, we get a positive. Plugging that into the second factor, we also get a positive, and a positive times a positive is a positive. So for any x value in this region, we would get that this product is positive. Now, what we are interested in for the domain here is when this product is either greater than or equal to 0. Now, right at the value of -2, it's equal to 0, and at the value of +2, it's also equal to 0. So what we want to take are the regions where this product is either positive or 0. And so in this case, the domain is going to be from -infinity up to and including -2, union, including the 2, because that's where it's 0, to +infinity. So this is the domain of this function. And remember, we know that radical functions are continuous on their domains. So we can say that h of x is continuous for x on the interval -infinity to -2, inclusive, union 2, inclusive, to infinity. Next up, we have the intermediate value theorem, which you can abbreviate IVT. If these conditions are met, first, f of x is continuous on the closed interval from a to b. Let's look at this diagram. We see that from a all the way over to b, including the endpoints, we can draw that graph without having to pick up our pencil. So f is continuous. We can see that by looking at the graph on this interval from a to b. Second, f of a cannot equal f of b. So that's just saying that the y values of the endpoints have to be different from each other. And we can see that f of a is up here, f of b is down here. So they are different. Third, k is between f of a and f of b. Now remember, these are y values, so that means k is also a y value. So suppose k was here. It could be anywhere between f of a and f of b. Then, if these three conditions are met, then it is guaranteed that there exists a c on the interval from a to b such that f of c will equal k. Remember, a to b is an interval on the x-axis, so c is an x value. And this is just saying that somewhere in between a and b, there will be at least one x value of c, where if we plug it into the function, the y value will be k. So what the intermediate value theorem is saying is if you have a continuous function on a closed interval and the y values of the endpoints are different from each other, it's guaranteed that if you get from this y value to this y value, you at least have to go through all of these intermediate values on the way. Now in this graph, you can see we attain some other y values that are outside of the interval between f of b and f of a, and that's okay. The intermediate value theorem doesn't say anything about those y values. What this statement of the intermediate value theorem is saying is it's guaranteed that to get from this endpoint to this endpoint, we have to go through all of these y values. And if we have to go through all of those intermediate y values, then that means there will be an associated x value for those. Now let's take a look at what we have going in our diagram here. If we work off of this k, then this would be a value of c. Let's call it c1. This would also be a value of c in this case, so that's c2. And on this particular graph, there would be a third value of c. Right here, we'll call it c3. Now, the intermediate value theorem does not tell you how many values of c you will get. This statement right here just says that there will be at least one. Now, in writing these proofs using the intermediate value theorem, sometimes we make use of shorthand symbols. So we have a symbol that will stand for the words "there exists," another symbol that stands for "such that," the upside down A that you've seen before, which stands for "all," and the three little dots, which you've used quite a bit, for "therefore." And we will make use of all four of those symbols throughout writing proofs. For example, in the proof statement of the intermediate value theorem, we can replace "there exists" with this symbol here, and we can replace "such that" with this symbol. And it just saves you a little bit of writing. And if you prefer to just write out the words, that's always okay. Either way. In this example, use the intermediate value theorem to prove f of x equals x cubed plus x minus 13 has a root in the interval, which is a closed interval, from 2 to 3, or explain why it fails. Now remember, for a function to have a root, that means that the function is equal to 0 there. So the y value that we are looking for is 0. So in the context of the intermediate value theorem, this is our value of k. So now what we have to do is walk through the 3 steps. Step 1, we have to show that we have a function continuous on our closed interval. Now f of x is a polynomial, so it's continuous for all real numbers. So from negative infinity to positive infinity. Therefore, It will certainly be continuous on a subset of this interval, which is from 2 to 3. So we've satisfied step 1. Step 2 says we have to show that f of a is not equal to f of b. So in our case, we have to show that f of 2 does not equal f of 3. So we just need to plug these points in. F of 2 is going to equal 2 cubed plus 2 minus 13. And of course, that's going to equal 8 plus 2 is 10 minus 13, negative 3. F of 3 is going to equal 3 cubed plus 3 minus 13. So we have 27 plus 3 is 30. 30 minus 13 is 17. So here we've shown that f of 2 does not equal f of 3. So now we have satisfied step 2 of the intermediate value theorem. Step 3 is that our value of k, which remember, since we are finding a root, our value of k is 0, and we have to know that that's in between f of 2 and f of 3. Well, certainly 0 is between these two. So you can either write that out in words, or you can show that 0 is in between those two by writing this inequality. Negative 3 is less than 0 is less than 17. That shows that 0 is between these two. Or you could say 0 is between negative 3 and 17. So you can write it using symbols, or you can write it out as a sentence. So that satisfies step 3. So now, because we've satisfied steps 1, 2, and 3 of the intermediate value theorem, now we can make the conclusion. So by 1, 2, and 3, IVT applies, and there exists an x value, which is c on the interval from 2 to 3, such that f of c will equal 0. So we can't make this conclusion until we've shown that all 3 steps of the hypothesis have been satisfied. We could also write this conclusion using the symbols. Remember that we can replace there exists with this backwards looking E symbol. Let's replace this. I'll show you how you could write it. So we could say there exists a C, which is an element on the interval from 2 to 3 in that closed interval, such that f of c equals 0. And you are welcome to write out your conclusion using words, or you can write it out using the symbols. Either way is good. So let's make sure you understand what happened in this proof. We had to show that the function had a root meaning that the y value equaled 0 somewhere. Now, since we have a continuous function, and at one endpoint the y value was negative, at the other endpoint the y value was positive, what the intermediate value theorem is saying, of course it has to pass through 0 on the way from a negative to a positive. And the reason we know that is because we have a continuous function on our interval. So the only way to get from a negative y value to a positive y value on a continuous function is that somewhere you have to pass through y equals 0. And the place where that happens is at x equals c. In this example, use the intermediate value theorem to prove f of x, which equals the quantity x cubed plus 2 over quantity x minus 4, has a root in the interval from 1 to 2, or explain why it fails. Remember that having a root means that somewhere f of x would have to equal 0, and in terms of the intermediate value theorem, that would be our value of k. Now, step 1 says we first have to find out if we have a function that is continuous on our closed interval from 1 to 2. F of x is a rational function, and we need to exclude any x values that would make the denominator 0. So f is continuous from negative infinity to 4 union 4 to infinity. We have to exclude 4 from the domain. Well, certainly the interval from 1 to 2 would fall within this interval, so therefore we can conclude that f will be continuous on the closed interval from 1 to 2. We can't just say this without justifying why we know it's true. Because f is continuous on this interval, we know that it will be continuous on this smaller interval, which lives completely inside one of these intervals. Step 2 says we have to show that the y values of the endpoints are different from each other. So we need to look at f of 1 and f of 2 and show that they are different. So in step 2, we do f of 1, which is going to equal 1 cubed plus 2 over 1 minus 4. Well, this works out to be 3 over negative 3, so that equals negative 1. F of 2 is going to equal 2 cubed plus 2 over 2 minus 4. So that's going to be 10 over negative 2, which is negative 5. And certainly those two values are not equal to each other, so f of 1 does not equal f of 2, and so that satisfies step 2. Then we go on to step 3, and we have to show that our value for k lives in between f of a and f of b. So we would have to show that 0 falls between negative 1 and negative 5, and certainly that is not true. So in this case, this function fails the intermediate value theorem's hypothesis at step 3. So we would say 0 is not in between -1 and -5. So therefore, the IVT does not apply. In this example, find the value of C guaranteed by the intermediate value theorem, or explain why it fails. We are given f of x is the quantity x squared plus 1 over quantity x plus 6 on the interval from 0 to 3, where f of c is equal to 5/8. Now, in terms of the intermediate value theorem, this 5/8 is the value of k. So that's the y value where we will have to find c, which is the x value at that y value. Now let's walk through the steps of the hypothesis of the intermediate value theorem. First, we have to show that f is continuous on this interval from 0 to 3. We know rational functions are continuous on their domains. We have to exclude any x value that would make the denominator 0. So that means f is continuous everywhere except at -6. So we say from -infinity to -6, union -6 to infinity. Therefore, we know that f will be continuous on a subset of this, which is the closed interval from 0 to 3. And once again, we can't just say this without justifying why we know it's true. We know that f is continuous on this interval, therefore it will be continuous on a subset that lives completely inside one of the other intervals. Step 2, we have to show that f of 0 and f of 3 give different y values. So f of 0 is equal to 0 squared plus 1 over 0 plus 6. So that's equal to 1/6. F of 3 is equal to 3 squared plus 1 over 3 plus 6. And so that's equal to 10/9. And certainly these are different values, so we are able to say that f of 0 does not equal f of 3. So that satisfies step 2. Now in step 3, we have to decide if our value for k, which we know is 5/8, lives between f of 0 and f of 3. And certainly 5/8 is in between 1/6 and 10/9. So remember, we can write that as an inequality. 1/6 is less than 5/8 is less than 10/9. Or you can write that out in words. So you could say 5/8 is between 1/6 and 10/9. Either way you want to say this is fine. Now that satisfies step 3, and because we've met all 3 requirements of the hypothesis of the intermediate value theorem, we get to make its conclusion. So by 1, 2, and 3, the intermediate value theorem applies, and there exists a C on the interval from 0 to 3 such that f of C is going to equal 5/8. And now, of course, if you prefer, you can write out the words. So this one would be there exists, and this one would be such that. Okay, so now we know that the intermediate value theorem applies, and in this problem, we have to actually find the value of C where this happens. So let's do that next. So now we have to solve this equation and find the value of C. F of C would be C squared plus 1 over C plus 6. Because remember, f of x was just x squared plus 1 over x plus 6. So if we're plugging in C for the x, we get this expression. And we have to set that equal to 5/8. So now let's go ahead and cross multiply. We would have 8 times the quantity C squared plus 1 has to equal 5 times the quantity C plus 6. Distributing, we get 8C squared plus 8 is equal to 5C plus 30. Gathering all the terms on the left-hand side, we have 8C squared minus 5C minus 22, and then equals 0 over on the right-hand side. So now we need to factor this, and you can do this by whatever factoring method you like. We know that 8C squared, we could take C times 8C, put in our little cross beams, and to make negative 22, we can go negative 2 times 11. Now when we do the cross products here, 8C times negative 2 gives us negative 16C, and C times 11 gives us 11C, and when you add those up, you get negative 5C, which is exactly the middle term that we needed. So then this tells us that we will take the quantity C minus 2 times the quantity 8C plus 11 equals 0. So this is the factorization of this quadratic. And we can always FOIL it out to check C times 8C is the 8C squared. Outside, we have 11C. Inside, negative 16C. That gives us our negative 5C here. And then negative 2 times 11 is the negative 22. Now, using the zero product property, we set each of these to 0. And solving each of these, this first one, we get C is equal to 2. And for this second one, we would subtract 11 and then divide by 8. So we have C is equal to negative 11/8. Now, remember the interval that we're solving on is between 0 and 3. So negative 11/8 is not in that interval. So we have to exclude that one. You will need to say negative 11/8 is not an element of the interval 0 to 3. So reject it. So therefore, our solution is C equals 2. And so by applying the intermediate value theorem and solving f of C equals 5/8, we found out that on our interval from 0 to 3, this will be true when C is equal to 2.